Here we're going to look at a definition, and we see that a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Math is kind of compact, or sometimes very compact. So let's unpack what this definition says. There are basically three parts to this equation here. Number one, we have that the limit as x approaches a of f of x exists. That means we don't have a situation where the limit from the right doesn't match the limit from the left. It also means that we don't have, say, a vertical asymptote at a. I should say at a. This is all at a, right, at a particular x value. Number two, f is defined at a. And so that means we don't have a situation where we have like a hole in our graph at a. Now, since I could have a limit at a where there's a hole, and I can define f at a placing a point off of where the limit is, we have the third part of the definition, which basically says the limit value is the same as the function value. So we don't have any gaps. We don't have a vertical asymptote at a, again, at a, and we don't have a hole, whether there's a point off of the hole or not. That's what it means to be continuous. You knew what continuous was already, though. You might think, well, continuous means you can draw it without picking up your pencil. And that's right. But there are no pencils in mathematical definitions, so we have this formal thing here. I end up redrawing all of those pictures because we're now going to look at types of discontinuity. And our three pictures are this one where there's a jump in f at a. There's one where we've got, say, a vertical asymptote. And it doesn't matter if the branches of the function as they approach the asymptote are both pointing towards positive infinity, negative infinity, opposite directions. It makes no difference. And then we have the situation where we have a hole. Let me go ahead and label A for all of these. And in the first, in the case of the first picture where we have a gap in y values from the left and from the right, a different limit from the left as is the limit from the right, that's called a jump discontinuity. The type of discontinuity associated with a vertical asymptote is called an infinite discontinuity. And the type of discontinuity where you have a hole in a graph, whether or not the function is defined, say there's some point that's off of the hole, whether or not that point is there, as long as the hole is there, this is called a removable discontinuity. And it's called a removable discontinuity. Let's say the limit is has a value of L. It's called a removable discontinuity because we can say like f of x is equal to, whatever it is, as long as x is not a, and then it's equal to L if x is equal to a, and you're basically putting a point where the gap is, and you're fixing the discontinuity. There's nothing we can do to fix a jump or infinite discontinuity. Now I want to point out that the discontinuities are all occurring at a, right? This first one with the jump discontinuity, it's continuous everywhere except for a. And the one with the infinite discontinuity, it's continuous everywhere except for where that vertical asymptote is. And likewise for the removable discontinuity, it's continuous on other intervals. And that idea is going to lend itself to what types of functions are continuous. Types of functions that are continuous on their domains are polynomial, rational, radical, logarithmic, exponential, trigonometric, and algebraic combinations of these. And when I say algebraic combinations, what I mean is addition, subtraction, multiplication, division, and composition. Polynomial functions include constant and linear. And if you think of the graph of a constant linear polynomial function, exponential, logarithmic, sine and cosine, you can clearly see that those are continuous everywhere. a rational function and 6 of the trigonometric functions have asymptotes, and these functions are continuous everywhere they don't have an asymptote. I just misspoke. A logarithmic function has an asymptote as well. So that's in the category of trigonometric and rational, because we have those asymptotes continuous everywhere where there's not the asymptote. Or in the case of a logarithmic function, continuous everywhere on one side of the asymptote. The category of radical functions is a little bit different, and we're going to consider that now. If we consider y equals the square root of x, its graph is of course half of a parabola on its side, and the limit as x approaches 0 of the square root of x does not exist, because a limit is a two-sided thing, right? There's no function to the left of 0 for the square root function. But we can say that the limit as x approaches 0 from the positive side of the square root of x does exist. It's equal to 0, which is equal to the square root of 0, right? So the limit value is equal to the function value if we consider only a one-sided limit. And so we would say that y equals the square root of x is continuous at 0 from the right. So if we need to consider only a one-sided limit, then we can consider continuity from that side.